All right, so 2.5 is called implicit differentiation. And we're going to be doing differentiation here, so all the same techniques that we've been learning, but in a slightly different environment. There's also a component of this when we get to it next class period at the end that's a throwback into 2.2 and 2.3 with some applications of derivatives that I had saved until now here because they didn't really fit in with the gateway stuff we were focusing on, and they seem to fit here a little bit better for our purposes. So to start with, what you've been doing is taking explicit derivatives. We haven't called them that, we just call them derivatives. So this is taking derivatives of y in terms of x when an equation can be simplified with y equals on one side and all the x's on the other side. So that fits the description of what we've been doing. We have y on one side, we have all the x's with whatever operations we're working with on the other side, and we've moved forward in that way. Implicit differentiation happens when we have x's and y's on the same side of the equations together. Okay? So in particular, these are usually not functions, or even if they are, they're sometimes just not easy to be solved for y. So these are taking derivatives of y in terms of x when it cannot be simplified with y equals on the other side. Sometimes it can be, it's just easier to do it this way, by the way. And we'll see one of those at some point in our 2.5 one as well. In order to do this method, we treat both x and y as variables, and we use all the derivative rules we have learned. There's at least 3 different ways to talk about doing implicit differentiation. So I'm going to show you the way that I teach, and I teach it this way every single time I do, and that's fine. There are other ways that some people might describe or work with you at in the Success Center. If you like those better, that's fine too, as long as you can utilize them and work through them effectively and correctly. I feel like this one is the most intuitive for what we've already done, and it falls along most closely. So here's an example of one. It's x squared minus y squared equal 25. As you can see, the x and the y are on the same side of the equation. Okay. Now, technically, could we solve this for y? We could. But if we solved it for y, we'd end up with a square root involved, and we'd end up with a plus or a minus. And that's very messy. And honestly, this one solves really easily with implicit differentiation, whereas if we solved it for y, it'd be really messy. So this is an example of one that while it could be solved for y, it simply isn't the easiest approach. Does anybody remember what this is an equation of? You would have seen it, I think, in trig. Close. If it was a plus, it would be a circle. It's minus. What's that? Ellipse. You're really close too. An ellipse is another option. Ellipses also have a positive between them. It's a different kind of conic, huh?
What?
A different kind of conic. Does anybody else remember?
That was one nice.
It is a conic, yeah. It's called a hyperbola. Hyperbolas, generally speaking, depending on how they're written, either look like this or they look like this. Whoa, that doesn't look good, like that. So it's a hyperbola. That's just extra for today. You didn't really need to know that, but that is what the equation is. All right, so here's the way this works. X squared's just like it always was. What's the derivative of x squared? Yes, 2x. Sorry, I'm trying to bring up my screen guard. All right, 2x. Now, we haven't done a derivative written as y squared, but what would you imagine it is? 2y. Okay, it is 2y, but think about what happens when we normally have y equals all this stuff, and we take the derivative. What is the derivative of y? Well, it's y prime, or dy dx. Because I don't want us to lose the prime associated with the y, I'm going to write what I'm about to write down as dy dx. But if you really want to use the y prime, you can. It's okay. I've taught it that way and done it before that way too. But I don't want to lose the y prime, and I'm afraid that we might. So whenever we take the derivative of y, even if there's y squared to start with, and we do it to 2y, the next thing we do is we say, what is the derivative of y? And the answer is dy dx. So here's the deal. We're treating this like it's a chain rule. The y squared, the squaring part, is the outside function. We bring the 2 down, we rewrite to the power 1. And then we take the derivative of the inside, that is the derivative of y, and the derivative of y is dy dx. It's a chain rule. Okay, the other side's easy. What's the derivative of 25? 0. Okay. And then the ending part of this problem is to solve this for dy dx. So we will shift one piece or the other to the other side. Since it's negative, I'm just going to move the 2y dy dx to the right. And then we would divide by the 2y so that these eliminate one another, right? And we would have that dy dx is equal to x over y. Sorry, guys. We're so close to people's offices, sometimes we get some background noise. Okay. Is that okay? It's a little weird, but is it okay? All right, let's try another one. This one, a little more complicated than the last one. But it's also an option to rewrite this a little bit before we start. In particular, notice y is on both sides, right? I mean, x is too, but the y is what I'm focusing on right now. Y is on both sides. On the left-hand side, there's a quotient. On the right-hand side, it looks kind of like the last one we did, so we could treat it that way if we wanted to. So we either are going to have to do a quotient rule on the left-hand side, or option number 2 is that we can multiply both sides by y, so that we don't have the quotient rule. And in doing so, we're going to create a product rule on the other side. So either way, we're going to have one of the rules we have not done before. Okay? So I think what I'd like to do is to show you both ways of doing it. I don't always do that, but I think I'm going to do it that way this time, so that you can see that they both have sort of some niceness to them, and they both have some messiness to them. And it's kind of just, 6 one way, half a dozen the other. It doesn't really matter. It's your choice. I'm going to do it exactly like it is first. It's going to be a quotient rule, and we're going to do it that way. Okay? So on the left-hand side, I have a quotient. The quotient rule says I take the denominator times the derivative of the numerator. So that would look like this. Y times x plus 3. And then I subtract the numerator. I didn't write that right. Sorry. Denominator times the derivative of the numerator, which would be 1. Minus, and then the numerator, which was x plus 3, times the derivative of the denominator. What's the derivative of the denominator? Yeah, dy dx. Yeah, you got it. dy dx. It's the derivative of y, which is dy dx. Or y prime if you want to be real careful. And then the denominator is y squared. Okay, denominator squared. The other side, because we worked with the hard side first, honestly, we did, is pretty straightforward. Derivative of 4x is 4. And we already did the derivative of y squared on the last slide. What is the derivative of y squared? 2y dy dx. Okay, so this one has the not niceness where I do have a quotient rule on the left. The other thing at this point now is that I have dy dx in 2 locations, and they're not even on the same side of the equation. I have to solve this for dy dx. So I got to shift some things around to get the dy dx's together. So we've got a little bit of algebra simplification, and one of the things we're going to have to do is multiply by that y squared. Because right now, that y squared is keeping me from being able to clean up the numerator and have it stand alone. So the first thing I'm going to do is I'm going to multiply by y squared. So on the right-hand side, this will be 4y squared plus 2y cubed dy dx. On the left-hand side, of course, these cancel, which is why I chose to do that. And just so I can save us a little bit of a step, I'm going to take these and I'm going to distribute the dy dx through. Okay, dy dx is being multiplied by each one of those. So I have y, and then I have minus x dy dx. And then I have another minus because there's a negative in front of the x and the 3. And so I have negative 3 dy dx. And on the other side, I still have my 4y squared plus 2y cubed dy dx. I need to collect all the dy dx's on one side and everything else on the other side. Because these are both negative, I'm going to move them over to the right-hand side. And I'm going to move this 4y squared to the left. So there's a y over here already. I'm going to subtract my 4y squared to move it to the left. There's a 2y cubed dy dx on the right. And I'm going to add my x dy dx and my 3 dy dx to the right. Okay, is everybody good with that? We are doing just algebra at this point, but it looks different because of the dy dx. Here's the deal. Once we have dy dx all on the same side, and it's the only thing there, like every term on the right-hand side has a dy dx, we can factor the dy dx out. So I can pull dy dx out of every term. That leaves me with 2y cubed plus x plus 3. What would my last step be? Yeah, divided by the stuff that's in parentheses, the stuff that got factored out of the dy dx. So I will divide both sides by 2y cubed plus x plus 3. And my final answer then for dy dx is that it's equal to what's on the left, which is y minus 4y squared over 2y cubed plus x plus 3. So that's dealing with it as it's currently written. Option number 2 is to multiply the y to both sides to start with, okay? So coming over here, I'm going to go back to the original problem, but I'm going to multiply the y to both sides. So I've got y times x plus 3 over y plus, equals 4x plus y squared times my y. So on the left-hand side, of course, the point in doing that is it canceled, leaving me with x plus 3, which is really a very nice thing to have on the left-hand side now. And now I have 4xy plus y cubed. Okay, at this point, we're going to take a derivative. What's the derivative of x? 1. What's the derivative of the 3? 0. So I have a 1 on the left. On the right-hand side, though, I'm going to have a product rule because I have 4xy, and x and y are both being treated like variables. So the product rule says that I rewrite the first piece, 4x, and I take the derivative of y. What's the derivative of y?
1.
It's 1 dy dx. Yeah, so you can write the 1 if you'd like. The dy dx is the part that's going to remain attached. Plus, then we need the derivative of 4x. What's the derivative of 4x? 4. And the y stays written there, right? Derivative of 4x times the original part of y. And then I need the derivative of y cubed. Now, we haven't found the derivative of y cubed, but we've done something similar. What's the derivative of y cubed?
3y to the power 2 dy dx.
Right. 3y to the power 2 dy dx. Now, I do have the dy dx is on the same side, but there is a piece of that doesn't have a dy dx with it, right? That piece has to move. So that 4y that's on the right has to move to the left before I can do anything else. So 1 minus 4y equals 4x dy dx plus 3y squared dy dx. And now these both do have the dy dx in them, so I can factor that out. So this is 4x plus 3y squared. And we will be dividing by 4x plus 3y squared. And the interesting thing that happens is it doesn't quite look like the same answer that the other one gave us. But it is. Dy dx equals 1 minus 4y squared divided by 2y cubed plus x plus 3. And the reason it doesn't quite look the same has to do with the fact that we don't know what the y value is. Sorry, I wrote it down what I had the other one on, didn't I? Sorry. What's my denominator? Thank you. I was just copying the wrong slide. I was looking at the wrong piece. 4x plus 3y squared. There we go, sorry. They're both correct. I'm not really sure that either one's any easier than the other one. They're both pretty messy, but they're two distinctly different ways of doing the problem. And we're going to stop there for today.